These are notes for Unit 2, Introducing Proportional Relationships. This is Lesson 5, 2 equations for each relationship. For each, it should be relationship, not relationships. And there are 2 equations. There's 2 properties in these proportional relationships, and there are 2 equations that you can write based on those 2 properties, and we'll get into that. The first activity, though, it's called missing figures. It is this image. As figure 2 is this image, figure 4 is this image, and it asks what's figure 1 look like and what's figure 3 look like, and then it says describe what the 10th figure in the pattern looks like. So probably lots of ways to do this. What I did is I looked at this, I'm looking for something that I can identify that is repeating, that I can make sense of. So I see 2 times 2 blues. So I see 2 blues, I see 2 of them. And that's in figure 2. And then I see 4 of those 2 blues in figure 4. Oh, that's pretty good. Then I see 2 of the 3 yellows. 3 yellows in figure 2. And 4 of those 3 yellows in figure 4. So that looks like it's the pattern. And if you look, figure 1 is going to be just 1 of the 2 blues and 1 of the 3 yellows. And figure 3 would be this one. It's going to be 3 of the 2 blues, 1, 2, 3, and 3 of the 3 yellows, 1, 2, 3. And there's something else going on, and that is what's on top and what's on the bottom. And so the even number of figures, it looks like it ends with 3 yellow rectangles on the top and 2 blue rectangles on the bottom. Whereas the odd number of figures, it looks like they end with 2 blue rectangles on the top and 3 yellow rectangles on the bottom. Now, I don't know if they mean for you to look at it that way. It's just the way that I'm looking at it. And so that means for the 10th figure, there's going to be 10 of these 2 blues. So 1 blue, 2 blues, and you just kind of count them up to 10. And 10 of the 3 yellows. 1 yellow, 2 yellows, 3 yellows, 4 yellows, and so on. And it's going to end, because it's an even number, it's going to end with the 3 yellows on top and the 2 blues on the bottom. So it's going to end like this, 3 yellows on the top and 2 blues on the bottom. So now I can draw it. And as you look at this more, you see another repeating unit. And that is this image right here. So you put these 2 together, and these are repeating. So it's this one, then this one, then this one, then this one, and then this one. There are 5 of those. So if this is the 10th figure, you can say that the repeat is the number of figures divided by 2. So it's the 10th figure. You divide 10 by 2. You're going to get 5 of these. So 1, 2, 3, 4, 5. Now what if it is 9, the 9th figure? So 9 divided by 2 is 4.5. So that would be 1, 2, 3, 4. And then the half is always the first part. And remember, an odd number figure is going to end with 2 blue on the top and 3 yellow on the bottom. So why are they having you do this? And the best I can figure out is that we're working on proportional relationships, and that constant proportionality is what repeats in these proportional relationships. It repeats X number of times. So if the constant of proportionality, let's say if X is 5, then that constant of proportionality is going to repeat 5 times. 5 times that constant of proportionality, whatever it is going to give you Y. If X is 7, then that constant of proportionality is going to repeat 7 times. So 7 times whatever that constant is going to give you Y. If X is 2/3, then that constant of proportionality is only going to be 2/3 of X. So it's not going to have a whole repeat. It's going to have just a fraction of repeat. So a lot of math is looking for patterns and looking for repeating things in those patterns. And that's basically what proportional relationships are. And that, I think that's why they're having you do this activity. And the second reason I can think of is that they're showing you a flipping pattern. So it's 2 blue, 3 yellow, and then 3 yellow and 2 blue. And we're going to flip the constant of proportionality to get that second equation as we go through these activities. So there's two equations, that's the title of this activity. And to get the second equation, we're going to take the constant of proportionality and flip it. And that's called the reciprocal. Again, I don't know if that's why that's in here, but it gives us an opportunity to talk about that. So this is activity 1. This is activity 2 from lesson 5, 2 equations for each relationship. And so the 2 equations in this case, one equation is going from meters to centimeters, and the other equation is going from centimeters to meters. So we're going to look for these 2 equations in these activities in this lesson. So activity 2. So the first part of this activity is going from meters to centimeters. And so if you have y centimeters over x meters, so we're going to label the column on the left x, column on the right y, and the constant of proportionality is going to be y divided by x, or y over x. And so there are 100 centimeters per meter. So this is the y value is centimeters, it's on the right side, and the x value is meters, it's on the left side. So y over x is 100 centimeters per 1 meter. So what that means is that centimeters to meters, there are 100 times the number of meters for centimeters. So centimeters are equal to 100 times the number of meters. Let me say that again. The number of centimeters are equal to 100 times the number of meters, because meters are big. You don't need very many meters to measure the same distance as centimeters. As a matter of fact, you need 100 times as many centimeters to measure the same distance that you measure in meters. So you're going to take the number of meters always and multiply that by 100 to get the number of centimeters. So centimeters is equal to 100 times the number of meters. So y equals kx, and k is, or the constant of proportionality, is 100. So all the way down this table, you're going to multiply every number of meters by 100 to change that to the number of centimeters to measure the same distance. So the second row is 94 hundredths times 100. Now I put these values here to show you that it is the digits of the number that are sliding 2 place values larger when you multiply by 100. I just don't like it when people say, oh, just move the decimal point, because the decimal point doesn't move. It always stays in the same spot. And if you talk about the digits moving 1 place value larger or 1 place value smaller, it keeps the idea of place value within the grasp of the student. The moment you start talking about decimals moving, it begins to remove the idea of place value. So if you just say this number, 94 hundredths, and write it you can even write it as a fraction, times 100, you end up with 94 centimeters. So you're sliding 2 place values larger because you're multiplying by 10 and then multiplying by 10 again. So it becomes 9 4/10, and then it becomes 94. So 94 hundredths times 100 is 94. This one is 167 hundredths. It ends in the hundredths place, so you can end that name with hundredths. So 167 hundredths times 100 equals 167. And again, it slides 2 place values larger, 2 place values to the left. I think I may have said to the right up here, but you're sliding, as you go to larger place values, you're sliding to the left. So this is 16 7/10, and this is 167 as you multiply by 10 and then multiply by 10. The last one is 5,724 hundredths times 100 equals 5,724. So you slide these digits 2 place values to the left. So this is 572 tenths. Slide each one of these 1 place value to the left when you multiply by 10. and then another place value to the left when you multiply it by 10 again. So this is 5,724. 5,724. And if you multiply x, whatever value you have for meters, multiply that number by 100, because you have 100 times as many centimeters to measure that same distance that you're measuring in meters. So y, this right column, equals 100 times the number of meters that you have. So y equals kx is the general form of the equation, and the specific equation for this relationship is y equals 100x. So that's one equation. The second equation is on the right side here, and what they did is they just switched the columns. And now they called this column on the left the y column and this column on the right the x column. I wish they hadn't done that. I wish they just had kept them the same. And this could be an activity that you do as an extension, is rewrite this problem or do this problem with the y column being where it should be, which is on the right, and the x column on the left, and you'll get the same thing. And what they're going to do is they're going to show you that you multiply this way, the constant of proportionality is now going to be 1/100th, because you need 1/100th as many meters, the number of meters that you need to cover the same distance as you cover with 100 centimeters in this case. So, but everything gets reversed, and if they had just left this as the y column and put these values over here, you're going to go in this direction, which is what you're going to do in the future. You're going to have a table like this. You're going to have some values on the left, some values on the right, and you're going to realize that when you multiply this way, you multiply by the constant of proportionality. When you multiply this way, giving away the idea of the lesson here, you're going to multiply by the multiplicative inverse of that constant of proportionality. So we can look for that. All right, so you have to keep track. Now you have to realize that the column that's on the right is labeled x. So that's going to be x over y. X divided by y is going to be your constant of proportionality this time. A little bit different. That's why I wish they hadn't done it this way. But x over y is going to be meters. Meters are x, y are centimeters, and that relationship is 1 to 100. I'm sorry, 1 to 100, or 1/100th. So the number of meters is equal to 1/100th the number of centimeters, because centimeters are small, so you get a whole bunch of them. As a matter of fact, you get 100 times as many meters as you have, number of meters. And so the number of the number of meters is 1/100th the number of centimeters. So the constant of proportionality is 1/100th. You can write that as a decimal if you want, 1/100th. So now you multiply 100 times 100th, the answer is 1. And again, now you move the decimal point. Now you move the digits to the right as you leave the decimal point in the same spot, but now each of these digits slide one place value to the right, or one place value smaller, as you multiply by 1/10th. So 250 hundredths is 2 5/10. So this becomes 250 hundredths is the same as 2 5/10. So the 250 slides one place value to the right becomes 25. One place value to the right becomes 2 5/10. This one is 78 2/10 hundredths, which is 78 2/10 hundredths. A little bit weird to say. It's 782 thousandths. So this slides one place value to the right to get 7 82 hundredths, and one more place value to the right to get 782 thousandths. So 78 2/10 times 100th equals 782 thousandths, or 1/100th of 78 2/10. Okay, 1/100th, or 123 9/10 times 100th equals 1 239 thousandths. A little bit harder to say than just do. So slide these digits, all two place values, to the right, and you end up at 1 and 239 thousandths. All right, so if you have y, you multiply y times 1/100th, you get y times 1/100th, and that is equal to x. So x is equal to 1/100th y. So x equals 1/100th y, and notice that the relationship between this constant of proportionality and this constant of proportionality is that they are reciprocals. Now, if we had left the columns, if we had this column on the right side and this column on the left side, you'd end up with exactly the same thing, because you'd end up with, you'd be multiplying this way, so you'd end up with x equals 1/100th y. And you can go through that activity once again. All right, the point is that you have one equation going from meters to centimeters, and then the reverse, the opposite equation, goes from centimeters to meters. And in one case, you use 100 as the constant of proportionality. In the other case, to go the other direction, you use the multiplicative inverse of 100, which is 1/100th, which is also called the reciprocal. This is activity 3, filling a water cooler, and this is lesson 5, 2 equations for each relationship. And in filling a water cooler, it takes time to fill that water cooler, and that water cooler holds gallons. And so the relationship between these two properties is, in the first case, you can write that as 8 gallons per 5 minutes. So in 5 minutes, you have filled the water cooler with 8 gallons, or you can write this as 5 minutes per 8 gallons. And we'll get to that second relationship in just a moment. So 8 gallons per 5 minutes. Well, that's W is the number of gallons per the amount of time, which is 5 minutes. And that relationship is 8 divided by 5, or 8/5. So the amount of water that you fill into the water cooler is 8/5 the number of minutes. So once again, the number of gallons in the water cooler is 8/5 times the number of minutes. So that equation is the number of gallons in the water cooler is 8/5 times the number of minutes, or 8/5 t. Now notice that the number of gallons is larger than the number of minutes, because that's this number right here is larger than 1. So you're going to increase the number of gallons compared to the number of minutes by 8/5. And 8/5 also can be rewritten as this decimal value. So 2 times 8 is 16, 2 times 5 is 10. So this is 16/10, which is the same as 1 and 6/10. So one way of looking at this relationship in one equation is that the amount of water equals 8/5 the amount of time. The other way to look at this equation, or this relationship, is 5 minutes per 8 gallons. So you're standing there and you're filling it with 8 gallons. How long did that take? Well, it took 5 minutes. In the first case, you're standing there for 5 minutes. How many gallons did you gather, or did you fill it in 5 minutes? That answer is 8 gallons. So there's different questions, and this is flipping the relationship. I'm going to talk about that more and more in activities in the future. So 5 minutes per 8 gallons, that's time 5 minutes per gallons, 8 gallons. So that's the amount of time that it takes to, is 5/8 the number of gallons that you fill the water tank, the water cooler with. So time is equal to 5/8 the number of gallons. So notice that the number of the amount of time is less than the number of gallons. It's 5/8 the number of gallons that you fill the water cooler with. So the amount of time is 5/8 the number of gallons. The amount of time is 5/8 the number of gallons, and 5/8 is equal to 625 thousandths. And you can go through some, we could go through some ways of figuring that out. One to start, one way to look at it is that 4/8 is a half is equal to 5/10 or 500 thousandths. Then you have to add another 125 thousandths, and you might know that that's 1/8. 2/8 is 1/4, which is 250 thousandths, and half of that, which is 1/8, is 125 thousandths. Anyway, we could write that out and talk about that, but just on a calculator, figure out on a calculator, 5 divided by 8 is 625 thousandths. All right, so they're asking you which of these equations over here match this relationship between gallons of water and time in minutes. And so this is one equation. Gallons, W is equal to 1 6/10 T, and that's A. So A matches. B does not match. B is the opposite relationship, but gallons is not a fraction of the amount of time. Actually, gallons is larger than the amount of time. And time is equal to 1 6/10 W. Time is equal to, that's not correct, because the time is actually a number that's smaller than the number of gallons. So this can't be true. This would give you an amount of time that's larger than the number of gallons. And finally, D is correct. So time is equal to 625 thousandths times the amount of water. So that matches this equation right here. So A and D are correct. And one more time, the amount of water is greater than the amount of time. So the amount of water is greater than the amount of time. It gets multiplied by a number that's larger than 1. And the amount of time is less than the amount of water. This gets multiplied by a fraction that's less than 1. It brings the time down to a value less than the amount of water. And you can play around just a tiny bit to convince yourselves that 1 6/10 is equal to 8/5. 1 6/10 is 16/10. So you divide each of these by 2. That's equal to 8/5. And you could also play around with the 625 thousandths. Write it as 625 thousandths. Divide each of these by 5. That's 125 over 200. Divide each of these by 5. That's 25 over 40. And divide each of these by 5. That's 5/8. So 5 divided by 5 divided by 5 is actually dividing by 125. So 6 divided by 125 is 5. And 1,000 divided by 125 is 8. And so the two equations are that the amount of water is equal to 8/5 times the amount of time. So this is the constant of proportionality, 8/5, and that's going to give you a number that's greater than the amount of time. And the other relationship is that the time is 5/8. It's a fraction of the amount of water. So this is the constant of proportionality for this equation. And so notice that the amount of time that you get is less than the amount of water, because the constant of proportionality is a value that's less, is a factor that's less than 1. So it's going to be a fraction of the amount of water. So the constants of proportionalities are multiplicative inverses of each other. So 8/5 is a multiplicative inverse of 5/8. What that means is if you multiply them together, you will get an answer of 1. 5/8 times 8/5 equals 1, or 5/8 of 8/5 equals 1, or 8/5 of 5/8 equals 1. You can look at it either way. And another name for multiplicative inverses are reciprocals. They are reciprocals of each other. And the last part of this problem asks you, well, what if the rate of flow into the cooler is changed to 3 minutes per gallon? And which is faster, 3 minutes per gallon or the amount of time up here it takes per gallon? So let's figure this out first. 3 minutes per gallon means that the time, 3 minutes per the amount of water gallons, is equal to 3. So that means that the time is 3 times the number of gallons. It takes 3 minutes for 1 gallon. So this is 3 times the number of gallons. So the equation is time is equal to 3 times the number of gallons. Well, over here, which equation gives you time? It's this one right here. Time is equal to 5/8 the number of gallons. Well, that's a number that's less than 1 minute to get 1 gallon. So which is flowing faster? So time is equal to 3 minutes for 1 gallon, or time is equal to a little bit more than 6/10 of a minute for 1 gallon. Well, the one that's flowing faster is the second one. Time is equal to, and I'm going to write this as 5/8 of the number of gallons. So 1 gallon is 5/8 of a minute. So this is 5/8 minutes per gallon, and this one's 3 minutes per gallon. So this one is much faster. So you're filling the tank much faster. So just imagine standing there filling the tank with 1 gallon. So you have finished, if you're this one, you have finished in about a little bit more than half a minute. This one, you're still standing there for 3 minutes filling that 1 gallon. Now, how much faster is it? Well, again, you stood there for a little bit over a half a minute, got 1 gallon. So how many times are you doing that before you reach 3 minutes? Because each time you stand there and fill it for 5/8 of a minute, that's a gallon. Well, that's a division problem. You're asking how many 5/8 are there before I reach 3? And the answer to that is 3 divided by 5/8. You're answering the question, how many of these 5/8 are there to get to this 3? Well, 3 divided by 5/8 is equal to 3 times 8/5. So you're going to multiply, you're going to use the inverse operation, which is multiplication, and the multiplicative inverse. So you're going to multiply by 8/5. That equals 24/5 times as fast. Well, 24/5 is the same as 4 and 4/5 times faster. So you're going to get 4 and 4/5 times, actually you're going to get 4 and 4/5 gallons in 3 minutes. Whereas if you're filling it for 1 gallon for 3 minutes, you get 1 gallon, and at this rate you get 4 and 4/5 gallons because it's 4 and 4/5 faster. So just playing around with the numbers a little bit, trying to gain a deeper understanding of this problem. This is activity 4, feeding shrimp. And this is an optional activity, and it's a difficult activity, but it really gets into the details of these 2 equations. So if students spend a lot of time on this and go over and over it, think about it in great detail, it really builds an understanding of what's happening with these 2 different equations. So in the first part of the activity, it says that there's a shrimp, just a single shrimp in the aquarium, and it takes 1/5 of a gram of food each feeding to feed that shrimp. And there are 3 feedings each day, so it's fed 3 times each day. So the first question is how much food does that shrimp get fed each day? Well, if it's 1/5 of a gram per feeding times 3 feedings, then it's going to get 3/5 of a gram of food each day. So 3/5 grams. So let's complete this table down here. So the number of days is going to be the x value, and that's going to be labeled as D, days. And y is going to be the grams of food, and that's going to be using the letter F for food. And the constant of proportionality is the grams of food divided by the number of days. So how many days does it take to equal a certain number of grams of food? So y divided by x is the amount of food divided by the number of days. Well, that's 3/5 divided by 1 day. So the constant of proportionality is 3/5. So it takes, so the amount of food is 3/5 the number of days. So the amount of food is 3/5 times the number of days. So 1 day times 3/5 is 3/5 grams of food. 7 days times 3/5 is 21/5. Well, that's 20/5 plus 1/5, or 4 1/5 grams of food. 30 days is 3 times 30 is 90/5, and I would write that as 30/5, or 30 is 5 times 6 times 3, and that's all over 5 for fifths. The 5s cancel out, and you're left with 18 grams for 30 days. Now notice that the number of grams of food is less than, it's a fraction of the number of days. Actually, it's 3/5 of the number of days because you multiply by 3/5. So the equation is for x number of days, it's 3/5 x equals y. So for x number of days times 3/5 is 3/5 x. And that equals y. And that means that there's 3/5 of grams of food per day. And so the equation, I didn't write the equation. I should have written that the equation is food, F, equals 3/5 days. So F is y, so food equals 3/5 days. Now, if you go the other way, and you want to figure out how many days does it take to eat a certain number of grams of food, then you're going to multiply by 5/3. You're going to flip the relationship, and if you're going from grams of food to number of days, you're given a certain number of grams of food, how many days is that going to last? Then you're going to multiply by 5/3. So y going in this direction is going to be 5/3 times y to get the value of x, the number of days. So it's 3/5 of gram of food per day, and it's 5/3. And we're going to come back to this. This is the tough part. It's 5/3 days per gram of food. This is hard to think about. It's hard to kind of picture in your head. So let's take one example. If you want to talk about food per day, it's 3/5 of a gram of food per day. So you're going on a 5-day trip. So how much food do you need? So you're going to need 5 times this 3/5 of a gram. So 5 times 3/5 is 15/5. You're going to need 3 grams of food. So now you're leaving for 5 days. How much food do you need? 3/5 of the gram of food per day. On the other hand, what if you have a certain number of grams? Let's say you have 25 grams of food. How many days is that going to last? Well, it's 5/3 days per gram. So 1 gram will last 5/3 days. That's 1 2/3 days. And we're going to get into this in more detail. So it's 25 times that. So it'd be 25 times 5 divided by 3. So it'd be 125 thirds days for the 25 grams. All right, so we are flipping the relationship. We're going from 3/5 grams to 5/3 days. So it's 3/5 of a gram per day. We're going to go over how to do that in just a moment. So notice that 3/5 to 5/3. These are reciprocals. I won't get to that. All right. So x number of days, d is days, and f is grams of food. So here's the equation. So y is equal to 3/5 x. And so the amount of food is equal to 3/5 the number of days. Notice again that the amount of food is a fraction of the number of days, because you don't the amount of food is less than a single gram in a day. So it's a fraction. You use a fraction of a gram in 1 day. So the amount of food is a fraction of the number of days. So this is equation number 1. So days equals 1 day. Use 3/5 of a gram of food. Now you could rewrite this instead of 3/5 of a gram of food per 1 day. You could write 1 day per 3/5 of a gram of food. So you want to get this to 1 gram. So if you do that, you can divide the 1 by 3/5. You can do this division. So 1 divided by 3/5 equals 1 times 5/3. So you're going to use the inverse operation, which is multiplication, and the multiplicative inverse, which is 5/3. And you're going to get an answer of 5/3. So that tells you that days to food equals 5/3. So the number of days is going to be 5/3 the amount of food. So the number of days is going to be a number larger than the amount of food, because to use 1 gram of food, you're going to go for more than a day. Again, this is tough. So 5/3 days per 1 gram, which is 1 2/3 days per gram. On the other hand, it's 3/5 of a gram per day. So we're going to continue to look at this. Again, D is days, F is grams. So now we're going to go in the other direction. So 1 gram is 5/3 days. So the number of days is 5/3 the number of grams. So 1 gram, this is 1 5/3 times 1, is going to give you the number of days. So 1 gram is 5/3 days. And then F number of grams is 5/3 F days. So 5/3 the number of grams is going to give you the number of days. So this is equation number 1 up here. So the grams is equal to 3/5 the number of days, and the days are equal to 5/3 the number of grams. So days are more, it's a number larger than the number of grams. So this is equation 2. So the constant proportionality, this is 3/5 of a gram for each day, and this is 5/3 days for 1 gram. This is the unit rate, 3/5 of a gram for 1 day. So that's the same as 5/3 days for 1 gram. So 3/5 of a gram per day. This is 5/3 days per gram. So these are both unit rates, and they are reciprocals once again. All right, this is tough for me to think about, and you can probably tell I'm kind of struggling with how to explain it. What shows it nicely is a double number line. So I put together a double number line. This is days, this is grams. So on 1 day, how much food did that shrimp eat? It ate 3/5 of a gram in 1 day. So now I want to go backwards. I want to divide this up into equal parts so I can get out to 1 gram. So I'm going to divide this into 3 equal parts because it's 3 grams. So this is 1/5 of a gram. I'm sorry, it's 3/5 of a gram. This is 1/5 of a gram. That's 1/3 of a day. So you take this day and you divide that into 3 equal parts. So 1/3 of a day is 1/5 of a gram. 2/3 days is 2/5 of a gram. And 3/3 days, which is 1 day, is 3/5 grams. So in 1 day, that shrimp eats 3/5 grams of food. So how many days does it take to eat a single gram of food? So we haven't gotten to a gram yet, so it's going to be more than a day to eat a gram. So 4/5 grams, still haven't gotten to a gram, but that's 1 1/3 days, and that's the same as 4/3 days. And then you add 1 more fifth, 5/5 grams, that's equal to the 1 gram that we're trying to get to. Well, how many days is that? That's 5/3 days. That's 1 2/3 days. Now notice the 5/3 days is the reciprocal of the 3/5 grams. So when you go in one direction to figure out the number of days, the number of grams per day, it's 3/5 grams per day, but it's the reciprocal to get the number of days per 1 gram. So these are multiplicative inverses, which means if you multiply them together, you get an answer of 1, and they're also called reciprocals. So 3/5 grams, 5/3 days. Now that, just to make your life a little bit tougher, they say, well, what if instead of 1 shrimp in the tank in the aquarium, there are 10 shrimp? So now they're adding another property. It was just grams and days for feeding 1 shrimp. Now it's grams and days and number of shrimp. So they're adding another property, and you have to get this to 2 properties. It's the 2 properties that are proportional. And what's proportional in this case is the number of shrimp and the number of grams per shrimp. So it's 3/5 grams. So grams of food in 1 day. So this is grams of food in 1 day. It's 3/5 grams of food in 1 day. So that's the constant of proportionality. It's 3/5. So the amount of food in one day is 3/5 of a gram. So that equation is the food is going to equal 3/5 the number of shrimp. 3/5 gram per shrimp. I hope I said that correctly. It's the grams of food per shrimp. So this is 3/5 grams of food for one shrimp. So the amount of food is 3/5 the number of shrimp. So you make a little table here. One shrimp eats 3/5 of a gram of food. That's where we started. Two shrimp would eat 6/5 of a gram of food, because 2 times 3/5 is 6/5. That's 1 1/5 grams. So that's more than 1 gram for those 2 shrimp. And 10 shrimp would eat 30/5. So 10 times 3/5 is 30/5. 30 divided by 5 is 6 grams of food. So for those 10 shrimp, you need 6 grams of food. So the equation is the number of shrimp is equal to, the amount of food, is equal to 3/5 the number of shrimp. So the equation is the amount of food is equal to 3/5 the number of shrimp. And that makes sense. One shrimp is 3/5 of a gram. So the amount of food is a fraction of the number of shrimp. So it's less than the number of shrimp. So 6 grams is less than 10 shrimp. And as a matter of fact, it's 3/5 of 10. All right, now they're going to add another layer to this. What if you have 300 grams of food? How many days is that going to last you to feed 10 shrimp? So now you have 10 shrimp. Those 10 shrimp need 6 grams of food each day. So it's grams of food per day. So it's 6 grams of food per day. But we want to know how many days the 300 grams are going to last. So we actually want to know days per grams. So this is 6 grams per 1 day. This equation is the grams of food are 6 times the number of days. So the amount of food is 6 times the number of days. But we want to know how many days 300 grams are going to last. So we actually want to know the reverse. We want to know the reciprocal relationship. So instead of writing grams per days, we're going to write in 1 day, those 10 shrimp eat 6 grams of food. So now it's days per grams of food. So that's 1/6. So now the number of days is 1/6 the number of grams of food. So the number of days is 1/6 the number of grams of food. And that makes sense. If you got 6 grams of food, it's going to last you 1 day. That is 1/6 the number of grams of food you have. So notice that the number of days is a fraction of the number of grams. So the number of days, all right, so the number of days is 1/6 the number of grams. So days is equal to 1/6 the number of grams. And they're saying, I'm going to give you 300 grams of food. How many days is that going to last? Well, it's going to be, the number of days is 1/6 this 300 grams of food. So 300 grams of food divided by 6. Every time you take out 6 grams, that's equal to a day. So 1/6 of 300 is 50 days. A tough problem. All of this is pretty tough. So if you go through this, look at this, have students draw this double number line, think carefully about the unit rates, think carefully about grams of food per day or days per 1 gram of food. So days per 1 gram of food, or the grams of food per 1 day. Tough problem. Okay, this is activity 5, Flight of the Albatross. And this is the cool down problem for this lesson. And again, this is lesson 5, 2 equations for each relationship. So once again, we're going to look at those 2 equations. So there are two properties. One property is the distance traveled, and the other property is the time it takes to travel that distance. So you are given those two properties. One example. And so a large bird, albatross, a large bird that flies at 400 kilometers in 8 hours. So one property is the 400 kilometers. The other property is 8 hours. So 400 kilometers per 8 hours. So, and they give you this equation. The distance traveled is 50 times the number of hours. So it's in 1 hour, that albatross flies 50 kilometers. So it's 50 kilometers per 1 hour. And that's what you get. If you divide 400 by 8 hours, you get 50 kilometers per that 1 hour. So that is the constant of proportionality for this equation, in which you calculate the distance traveled given the time, given the number of hours. So distance per time is kilometers per 1 hour. So how far does that albatross travel in 1 hour? How many kilometers? So you have distance per time. Or you can flip that relationship and write it as time per distance. So what if you wanted to know how long it takes to travel 1 kilometer? So that would be the time per distance, or the time per 1 kilometer. So one relationship is the distance per 1 hour, and flipping that relationship, it's the time it takes to travel 1 kilometer. So this takes a lot of time to get used to thinking about flipping this relationship. So I'm going to show you a 2.5 minute, roughly a 2.5 minute video where I literally flip that relationship. So I'm going to start out with distance per time, or 400 kilometers per 8 hours, and I'm going to flip this to 8 hours per 400 kilometers. So here's distance per time. And so I'm just going to take the time and flip that over and write it as time per distance. So that means I have to rewrite the relationship as 8 hours per 400 kilometers. So I'm just going to move that up to the top to equal the time, and move this down to the bottom to equal the distance. So now we have time per distance is 8 hours per 400 kilometers. So 8 hours per 400 kilometers is in fact 1/50th of an hour per kilometer. So that relationship becomes 1 hour per 50 kilometers, which equals 1/50th. So the first equation, the constant of proportionality, was 50. And the second equation, when you go the opposite direction, that is 1/50th. So now this constant of proportionality is 1/50th. So the time that it takes to travel 1 kilometer is 1/50th of an hour. So now we're going to get time is equal to 1/50th times the distance. So notice that the time is a value that's a lot smaller than the distance. And that makes sense. 400 kilometers, 8 hours. So again, we're going to flip this, and so now we're going to be able to write the equation. So it's time per distance is equal to 1/50th. So the amount of time in this relationship is 1/50th the distance traveled. So if the albatross traveled 400 kilometers, 1/50th of 400 is that 8 hours. So the time is equal to 1/50th the distance traveled. All right, so I just literally reversed everything. And so I flipped that relationship from distance per time to time per distance. So in the one case, it was distance per time, how many kilometers per 1 hour, and I just flipped it to how many hours per 1 kilometer. So that's not very long. To travel 1 kilometer is not going to take very long. It's a fraction of an hour. It's 1/50th of an hour. So distance per time is 400 kilometers per 8 hours. Constant proportionality is 50. So the distance per time is, the distance is 50 times the number of hours. So 1 hour travels 50 kilometers. 2 hours travels 2 times 50, or 100 kilometers. 8 hours travels 8 times 50, or 400 kilometers. So in 1 hour, the albatross travels 50 miles. If you flip that relationship, now you're going to be able to answer the question, how long does it take? How much time does it take to travel 1 kilometer? Well, it's 8 hours to travel 400 kilometers. And if you divide this, 8 divided by 400, it's equal to 1/50th of an hour. So the time that it takes to travel 1 kilometer is 1/50th of the distance traveled. So the distance traveled is 1 kilometer. It takes 1/50th of an hour. So notice that the time, again, is much smaller than the distance traveled. So it's 1/50th of the distance traveled. And 1/50th is the same as 200ths. And so you can rewrite this as 200ths. And so in 1 kilometer travels for 1/50th of an hour. So just how long is 1/50th of an hour? Well, 1/50th of an hour is the same as 1/50th of 60 minutes. And that's 60/50ths of a minute, or 6/5 of a minute. Well, 6/5 of a minute is 1 1/5 minutes it takes to travel 1 kilometer. And 1/5 of a minute is 12 seconds. 5 times 12 seconds equals 60 seconds, or 1 minute. So in 1 minute and 12 seconds, the albatross travels 1 kilometer. And it takes an hour to travel 50 kilometers. It takes 50 times this long to travel 50 kilometers. So that's it. The two relationships are distance per time. Where is that equation? Is the distance equals 50 times the amount of time that you've traveled. So 50 times 1 hour, 50 times 2 hours, etc. And the second equation is the time is 1/50th the distance traveled. So if you travel for 1 kilometer, it's 1/50th of an hour. 2 kilometers is going to be 2/50ths of an hour. 50 kilometers is going to take 1 hour, 50/50ths. So it travels 50 kilometers in 1 hour, 1 hour per 50 kilometers. All right, so this is the cool down activity 5. This is the summary for lesson 5, 2 equations for each relationship. And I don't think I've been making the point strongly enough about those 2 equations that the constants of proportionality for those 2 equations are reciprocals of each other. They're multiplicative inverses. And this is the last activity that we just did. And in this case, it was distance is equal to 50 times the amount of time. So in this case, the constant of proportionality is 50. But the other equation, the opposite equation, if you're going to figure out time, time is equal to the reciprocal of 50. So this is 50. This is 1 over 50, or the reciprocal. So time is equal to 1/50th the amount of distance. So this is going the opposite way on the table. Instead of figuring out the distance traveled in a certain amount of time, you're figuring out the time it takes to travel a certain amount of distance. So that's the reciprocal relationship, and the constants of proportionality are reciprocals, also known as multiplicative inverses. And so in the summary, they use Kieran is riding a bike, so it's 10 miles per hour. So similar kind of problem. It's time, it's distance per time. So it's 10 miles per 1 hour. And they tell you this equation here, distance is equal to 10 times the number of hours. And so if you write distance per time is equal to 10 miles per hour. And so the distance per time is equal to 10. And so if you think about it, what that means when you do this division, that means that you'd have 10 of these t's
10 times t, 10 times the amount of time, to get the equivalent distance that goes with that amount of time. So distance is equal to 10 times the amount of time. So distance is equal to 10 times the amount of time. And the reciprocal relationship, if you're going to figure out, instead of distance, if you're going to figure out time, you're going to use the reciprocal of 10, or the multiplicative inverse of 10, which is 1/10. So now think about it for just a second. You're traveling 10 miles. It takes an hour to bike those 10 miles. So think about riding your bicycle for 1 hour. It's going to, in that 1 hour, you're going to travel 10 miles. You're riding. And the distance that you've traveled in that 1 hour is 10 miles. And so now you're asking the question, well, how long does it take for my bicycle to go 1 mile? You did ride 10 miles. It's a lot farther, but now I'm only going to ride a mile. So let's say your little brother or little sister goes for a ride with you and they stop after 1 mile. How long did that take? So it was, distance is 10 times the number of units of hours. And if you flip that relationship, now it's the amount of time to ride per 10 miles. So it's 1 hour per 10 miles. So how many hours is it for 1 mile? So how long did it take your sister, if she's riding at the same speed, to travel just that 1 mile before she got tired of doing this and gave up and went home? So the time is 1/10 the amount of distance. So the time is 1/10 the distance. So instead of 10 miles, she only traveled 1 mile, so it's 1/10 of an hour. And that makes sense. So you're going for your bicycle ride, you're planning on riding 10 miles, it's going to take an hour. Your little sister gives up after 1 mile, that's 1/10 of an hour. So how much time was equal to, so the time is equal to 1/10 the amount of distance. The distance is 1 mile, so the time is 1/10 of an hour. So remember that time is in hours for this problem, and distance is in miles. And also notice that the amount of time is a number that's a lot smaller. It's 1/10 the distance. So the distance was 10 miles. The amount of time was 1 hour. So the units, the number of units for time is a lot smaller than the number of units for distance in this problem. So time is 1/10 of the number of units of distance. So now if we get to the general form of the equation, so now we're back to this y equals kx. So in this direction of figuring out the distance is equal to 10 times the amount of time. So it's 1 hour, it would be 10 miles. So y is equal to k times x. So you divide y by x, that tells you how many of these k's of x you need to get to y. So y is equal to k times the units of x. But now if you go the other way, so now you're going to figure out the time it took to travel just 1 mile. So that's the opposite, or the reciprocal relationship. So the reciprocal of k is 1 over k, also called the multiplicative inverse. So now as x is equal to 1 over k times the units of y. So time is 1 over 10, 1/10, times the units of distance. So time is going to equal 1/10 hours to travel 1 mile. So x is 1 over k times the units of y. So you flipped the relationship. So you have to just look at this for a long time and think about it, and look at this for a long time and think about it. And what you're doing in these lessons is you're just putting these general forms of these equations into a context, into a story problem, so that they make sense for you. And the authors also talk about, if it's written this way, y equals kx. So y is proportional to the amount of x. So y is proportional to x. So if its distance is equal to 10 times the amount of time, that distance is proportional to the amount of time. So you're given a certain amount of time, and you go a certain amount of distance that's proportional. You're multiplying by the same value to get each of these. And x is proportional to the amount of y if you go the other way. So you're given a certain amount of distance. So what amount of time did that take? So time is proportional to the distance. Distance is proportional to the time. These things take a long time to kind of settle in your mind and get used to doing. These are the practice problems for lesson 5, 2 equations for each relationship. And in problem number 1, they just ask you about one equation and one constant of proportionality. And that is for the relationship between meters and kilometers. Now this is a fixed relationship. There are, if you measure 1 kilometer, then you have measured 1,000 meters. So it takes a whole lot of meters, because meters are small, to equal 1 kilometer, because kilometers are big. And so if you're given a number of meters, it's going to take 1/1000th of that number to equal the same number, to equal the number of kilometers used to cover that same distance. So the constant of proportionality is y over x, or 1 divided by 1,000, and that makes sense. Y over x is kilometers to meters is 1/1000th. So if I have a whole bunch of small things, to get the equivalent of those small things for a large thing, I need 1/1000th of these large things, kilometers, to cover that same distance. So 1 kilometer per 1,000 meters, that means that 1 kilometer is 1/1000th of the number of meters. So kilometers are 1/1000th the number of meters. So the number of kilometers are 1/1000th the number of meters. So 1,000 meters equals 1 kilometer. This is a small distance. There are a lot of them that cover that same distance as 1 kilometer. A kilometer is big, so you don't need many of those kilometers to cover that same distance. So we're going to multiply each one of these by the constant of proportionality, which is 1/1000th. Well, this makes sense. 1/1000th, 1,000 times 1/1000th is 1. So this is 3,500. Yeah, let's zoom in on this a little bit. 3,500 times 1/1000th. Well, that's 3 5/10. Now I wrote this again where I put the decimal point in one spot, and the digits slide 3 place values to the right to make this number smaller. So whenever you multiply by 1 over a power of 10, so 1 over 10, 1 over 100, 1 over 1,000, the number is going to get smaller. The digits are going to move to the right. So in this case, they move 3 place values to the right because it's 1/1000th. So you're multiplying by 1/10 3 times. 1/10 times 1/10 times 1/10. So 3,500 thousandths is 3 5/10. 500 thousandths is 500 thousandths. You just write the number as you say it. So this 500 slides over 3 place values to the right, 3 place values smaller. So it's 500 thousandths. 75 times 1/1000th is 75 thousandths. So you can just say it, 75 thousandths. So 75 slides over 3 place values to the right and ends up at 75 thousandths. Because you're multiplying by thousands, you can think of it as the ones place is going to end up in the thousandths place. So this 0 ends up in the thousandths place out here. This 0 ends up in the thousandths place right here. This 0 ends up in the thousandths place right here, 500 thousandths. And this 5 ends up in the thousandths place right here because it slides, once again, 3 place values smaller, 3 place values to the right. And 1 times 1,000th is 1/1000th. So again, that 1 slides 3 place values to the right, or 3 place values smaller. So the equation for this then is x times 1/1000th is 1/1000th x. So whatever the value of x is that you're given, I'm given so many meters. How many kilometers is that? You multiply that by 1/1000th. That tells you the number of kilometers. So the number of kilometers y is equal to 1/1000th the number of meters x. This is problem number 2. You have concrete building blocks. Each one of those blocks weighs 28 pounds. So think about that for a moment. That's pretty heavy, standing there with 28 pounds. You just have one block, a single block weighs 28 pounds. Use B for the number of concrete blocks and W for the weight. And it says write 2 equations. So when you see that, write 2 equations, think about flipping the relationship. If you start out that way, you'll never get it wrong. You'll be able to see what those 2 equations are going to be. One of the equations should begin with W, the weight. So you're calculating how much weight there is given a certain number of blocks. And the other one should begin with B, the number of blocks given a certain amount of weight. So B is the number of blocks, W is the weight. So it tells you in the beginning 28 pounds per one block. So that's weight per blocks, or W per B. So the weight is 28 times the number of blocks. Well, that makes sense. You have a single block, so you have a single block you're holding in your hands. How much does it weigh? It weighs 28 pounds, so it's heavy. And so notice that, so weight is 28 times the number of blocks, so W is equal to 28 times the number of blocks. B, every block weighs 28 pounds. So if I have 2 blocks, that's 56 pounds. 3 blocks, that's 84 pounds. 4 blocks, that is 112 pounds, I believe. 4 times 20 is 80. 4 times 3 is 32. Add those together, that's 112. So notice that the weight is a number that's much larger than the number of blocks. That's because each block weighs 28 pounds. It's going to be the weight's going to be 28 times the number of blocks. So if you flip that relationship, now it's blocks per pounds. So now I have the number of blocks is 1/28 the number of pounds. So if I have 28 pounds, how many blocks do I have? Well, I am holding in my hand 28 pounds. How many blocks am I holding in my hands? I'm holding 1 block in my hands. So 1/28 times 28 pounds equals 1 block. So the number of blocks is 1/28 the number of pounds. So how many blocks is it for 1 pound? Well, 1 block weighs 28 pounds. So take that 1 block and imagine, oh man, I can only use 1 pound of this 28 pounds. Well, you have to chop that up into 28 small pieces. So that means that 1 pound is 1/28 of a block. So the number of blocks is equal to 1/28 the number of pounds. Yeah, that's right. So 1 pound, and it takes a while. You got to just work through it. 1 pound is 1/28 of a block. So the number of blocks is equal to 1/28 the number of pounds. I only have 1 pound. I can only use 1 pound. So you have to imagine chopping that block up into 28 small pieces. So the 1 pound is going to be equal to 1/28 of a block. So note that the weight is a larger value than the number of blocks. As a matter of fact, it's 28 times larger. So the weight is 28 times larger than the blocks. So the number of blocks is 1/28 of the number of pounds. All right, again, flipping back and forth, and even I get confused. I have to think about it for a while, kind of sort things through in my head. So if you put the problems into this context, if you draw a block, so draw a rectangle, label it a block, label it 28 pounds. Okay, now imagine you just need 1 pound of that. So imagine chopping that block up into 28 small pieces. So 1 pound is going to equal 1/28 of that block. So blocks equals 1/28 of a pound, of the pounds. Okay, this is problem number 3. And so you have a length of rope and a cost for that length of rope. And the price is going to be labeled as P, and the length of rope in meters is going to be labeled as L. The price is in dollars. Price in dollars, and L is in meters. And so these two questions are the two different equations that you can write from this relationship. One is the price for a certain amount of rope. So you walk into a store, you buy a meter of rope, you walk up to the cash register, and you find out how much that costs you. So how much does the nylon rope cost per meter? So again, bought a meter of rope, how much does that cost? Or on the other hand, you might walk into the store with just $1. I have $1. I need as much rope as I can get for that $1. So how much rope can I get per dollar? So this B is per dollar and A is per meter. So let's work with the first one, A. Its price is equal to 80 cents, 8/10, times the length of rope. So they're giving you price per meter of rope. So P per L, or dollars per meter. And that price is 8/10 times the amount of rope, times the number of units of rope. So 8/10 times 1 meter of rope is 80 cents. Because remember, that price is in dollars, or 8/10 of a dollar, or 80 cents. So price is equal to 8/10. I'm going to write it as a fraction because the other equation is going to be the reciprocal of this constant of proportionality. It's going to be the reciprocal of 8/10. So you can see right away that that reciprocal is going to be 10/8. So that gets you pretty far just following that thinking. So price is equal to 8/10 the amount of rope. The price will be less than the meters of rope. As a matter of fact, it will be 8/10 of the meters of rope. So price is equal to 8/10 times 1 meter. 8/10 times 1 is 8/10 dollars, which is the same as 80 cents. 80 cents or 80 cents. All right, so that's A. Price is equal to 8/10 the amount of rope that you purchase. So price is equal to 80 cents per meter. All right, and if you flip that relationship, so now it's going to be the length of rope per price, or per dollar. And so that's going to be 10/8. So if you just write it as 10/8, 10 divided by 8, you can write that as 10/8. So the length of rope is 10/8 times the price. So you walk in with your $1, the length of rope I can get is 10/8 times that $1, or 10/8 meters. So the length of rope is 10/8 times the price, and 10/8 simplifies to 5/4. So the length of rope is 5/4 times the price. I have $1, the length of rope I can buy in meters is 5/4 meters. So 5/4 times that $1 is 5/4 meters. So that's 1 1/4 meters of rope I can get for that $1. Now this problem sets up nicely for a double number line. So if you draw that double number line, you're going to have 80 cents here, and that 80 cents, how much rope can you get for that 80 cents? 1 meter. So that's my starting point. And I'm going to zoom in on this number line so you can see what's going on. So my starting point, once again, is that 80 cents and 1 meter of rope. Now I divided that 80 cents up into 4 equal parts. Why 4 equal parts? Because I knew that one of these parts, 20 cents, I was going to need to get to $1. Because it's 80 cents for 1 meter rope, and how much rope is it for $1? So I knew I needed 20 more cents. Well, 20 cents is 1/4 of the 80 cents. So that kind of told me I'm going to divide this up in 4 parts. 20 cents, 40 cents, 60 cents, 80 cents. And so how much rope do you get for each one of those? Well, 20 cents, you get 1/4 of a meter. 40 cents, you get 2/4 of a meter, which is the same as half of a meter. 60 cents, you get 3/4 of a meter. And 80 cents, you get 4/4 of a meter, which is 1 whole meter. So this is 80 cents per 1 meter of rope. Okay, so now you're going to go another 1/4 of a meter, another 20 cents. So another 20 cents gets you to the dollar. Another 1/4 meter is 5/4 meters. This is 1/4, 2/4, 3/4, 4/4, 5/4. So that $1, for that $1, you can get 5/4 meters of rope or 1 1/4 meters of rope. So notice once again that the meters of rope is always greater than the price in dollars. So 1 meter, 80 cents. 5/4 meters, 1 1/4 meters, $1. So the length of rope that you get is always greater than the price in dollars, and you saw that in the beginning, in which 1 meter of rope cost 80 cents. Okay, this is problem number 4, and this is from an earlier lesson, lesson 4, from unit 2. And this is not asking for the 2 equations. This is just asking for one of the equations if they give you this table. And so it says, it's a proportional relationship. Find the constant of proportionality and write the equation for this relationship. So y is 2/3, a is 2. So if you're given 2 for a, you're going to end up with 2/3 for y. So what that tells you is that y divided by a tells you how many of these a's you need to get to an equivalent amount of y. So y divided by a is going to equal 1/3. Now, can you see that if you have 2 of something and you divide that by 2, you're going to get one of those things. So I have 2/3 divided by 2 is going to give me 1/3, because 2 divided by 2 is 1. And so now you can work it out mathematically or using the arithmetic. 2/3 divided by 2 is the same as 2/3 divided by 2. Well, 2 of anything divided by 2 is going to give me one of those things. And so the way to do this, again, using the arithmetic, is 2/3 times. So you're going to use the inverse operation, and you're going to use the multiplicative inverse. So you're going to multiply by 1/2. These 2's cancel out, and you're left with 1/3. Now, a constant of proportionality says that that relationship has to be the same all the way down this table. So for it to be truly a proportional relationship. So 1 divided by 3 is 1/3. That one's pretty easy. 10/3 divided by 10. Well, 10 of anything divided by 10 is going to equal one of those things. So 10/3 divided by 10 will equal 1/3. Again, you can go through the arithmetic. 10/3 divided by 10 is the same as that 10/3 times the inverse operation times the multiplicative inverse, or the reciprocal. So 10/3 times 1/10, these 10's cancel out, you get 1/3. And finally, 4/12 simplifies to 1/3. 4 times 1 is 4. 4 times 3 is 12. These 4's once again cancel, you get 1/3. So it's 1/3 all the way down the table. So that constant of proportionality is 1/3. So what that tells you is that y divided by a equals 1/3. So y is 1/3 of whatever a is. So think about a and think about taking 1/3 of that. So if we go back to the rope, the price, let's call y the price is 1/3 the meters of rope that you purchase. So in this case, you purchase 1 meter of rope. What's the price going to be? It's going to be 1/3 of that 1 meter. So 1/3 of 1 is 1/3. So the price is going to be 1/3 of $1. So this tells you y is 1/3 of a, so it takes 1/3 of these a's to get you to the equivalent amount of y. So y is equal to 1/3 a. So again, picture a, and you're taking 1/3 of that to figure out what the equivalent amount of units of y you need to get to that y. All right, so this is problem number 4. Okay, this is problem number 5. And for this problem, you have a map of Chicago, and they tell you that the scale on that map is that if you measure 1 centimeter on the map, then that's 100 meters in real life. So 100
centimeters. So the number of meters is 100 times the number of centimeters. So meters is 100 times the number of centimeters on the map. So measure 1 centimeter on the map, that's 100 meters in real life. So you measure 1 centimeter on the map equals 100 meters in real life. So if you measure 10 centimeters on the map, that's 1,000 meters in real life, and that's 1 kilometer. So to solve this problem, it says select all the statements that show or that express the same scale. So in each case, whatever you are given in the problem, change that to meters per centimeters. And then if it matches 100 meters per 1 centimeter, then it is the same scale. So for example, in the first one, it says 50 meters per 5 centimeters. So you measure 5 centimeters on the map, that's equal to 50 meters in real life. Is that the same scale? So they're saying 50 meters in real life for 5 centimeters on the map. So if you measure 10 centimeters on the map, if you double the 5 centimeters to 10, you have to double the 50 to 100. That's a different scale than what's given to you. What's given to you is you measure 1 centimeter, that's 100 meters. This scale is you measure 10 centimeters on the map, that's equal to 100 centimeters. So A does not match, it's a different scale. B, on the other hand, they say, all right, so we're going to give you 1 millimeter, measure 1 millimeter on the map, that's the same as 10 meters. So 1 millimeter on the map is the same as 1 millimeter on the map is the same as 10 meters. So that 10 meters, 1 millimeter is the same as 1/10 of a centimeter. So you have to know that. You have to understand that you measure 1 millimeter, that's a small amount, it's 1/10 of a centimeter. Well, how many meters is that then if you measure 1 centimeter? It's 10 times as much. So if you multiply that 1/10 centimeter, if you divide it by 1/10, that's 10 times 10 is 100. So actually what you're doing is changing this 1/10 of a centimeter to 1 centimeter. So you multiply by 10. So 10 times 10 is 100. So this 10 meters times 10 is 100 meters. So it's 100 meters per 1 centimeter, and that does match. And I made a little bit of a mess of this. I think going from here and just realizing, okay, if I multiply 1/10 of a centimeter by 10, that's going to give me to 1 centimeter. So I have to multiply 10 meters times 10 to get me to 100 meters. So that matches. C is 1 kilometer is represented by 10 centimeters. So this is C down here. 1 kilometer per 10 centimeters. Well, 1 kilometer is the same as 1,000 meters. So now I have to change this to 1 centimeter because that's what I'm starting with. 1 centimeter gets me to 100 meters in real life. So if I divide by 10 centimeters divided by 10 is 1 centimeter, 1,000 meters divided by 10 is 100 meters, and in fact that is the same scale. So measure 1 centimeter on the map, that's 100 meters in real life. And the last one says 100 centimeters is shown as 1 meter on the map. So you measure 1 meter on the map, that's going to show you 100 centimeters in real life. It's kind of funny actually. And so 100 centimeters divided by 100 is 1 centimeter. So that's 1/100th of a meter in real life. Actually, these are the same, by the way. Measure 1 centimeter on the map. That's 1 centimeter in real life. But anyway, so this is a very different scale. You measure 1 centimeter on the map. It's just a tiny amount that you go in real life. As a matter of fact, you only go 1 centimeter in real life, 1/100th of a meter. So this is a different scale than what's given to you. You have to get out 100 meters in real life if you measure 1 centimeter. So just the key to this kind of problem is making sure you understand where to start. It's 100 meters for 1 centimeter, and get all of these scales to meters per centimeter and see if it matches. If it matches, then yeah, it's the same scale. If it doesn't match, then it's a different scale.